So first of all, thank you so much for the opportunity to be here. It's truly delightful. It's been a very long pandemic, and I haven't seen too many friends of mine face to face in a long time. So it's really great to be here. Thank you, the department, the chair of the department, Mauro, and everybody who was involved in arranging my visit. So it's a great pleasure to be here. I was sort of thinking that I would like to tell you a little bit about COVID, just because it's something that that became one of the really important applications of many of the things that I've been working on over the last several years. I am very aware of the fact that there's lots of people who've been modeling COVID, and in fact, almost everybody now seems to be interested in doing that. So maybe some of the things that I do will remind you of some other models, of some other approaches that people have taken. But I will also try to emphasize where we were different and give you a little bit of the history of how this whole COVID project started. Please stop me if you will have questions, or if there is something that's unclear, I would be happy to answer. So I will start with basically, with basically showing you the map of the US from several months ago, where you can basically see that the colors are denoting a different amount of COVID in different parts of the country, and you basically see that there are some dramatic differences in coloring on that map, right? So we basically have the number of states, like over here in California, where at this time the number of COVID cases was very high, and then you had sort of the middle of the country when it was very little. So the point of this is to give you a sense that COVID, and at least in this particular setting, does not seem to be very uniform. It follows the people, but it also prefers some different geographical areas from each other. So the notion here is that sometimes we have to build models which are super complicated in order to be able to reliably make some predictions or models that have that level of complexity. But another approach to this is to try to build a flexible model which is probabilistic, which sort of averages out some of these features which are considered to be very, very diverse, and leads to some general ideas that help us understand what is happening. Okay, so that was the general notion. Keep having. Okay, so this is the early COVID, and this is Ohio. So just again to give you a sense what happened initially in Ohio. We had really COVID following the population centers. If you look at this map, and if you look at the different colors, this is the counties in Ohio, and this is the number of people who lived in different counties. Dots are showing the number of confirmed COVID cases, and this was very early on. This was in March 2020. So as you can tell, basically we see that at least early on, these dots were sort of following the density of the population in the entire state, which then basically tells you that at least initially, this map and this map were quite different. Here we're looking at things that are exactly following the population. Here we do follow the population, but there are some important exceptions. So as it turns out, modeling this kind of heterogeneity is easier than modeling the other. And I will talk about it some more. So in early March, I was asked by my university to help the governor's office. So they had, as I'm sure you also had, they had this emergency COVID response team, which was headed by the governor of the state of Ohio, and it was responsible for preparing the state for the pandemic. No one at this time really had a model that was immediately ready to go. So because I've worked on similar problems in the past, they asked me to help put it together. So that's what we did. And for the number of months early on, from maybe March until way into 2021, we did do that. So these are basically press conferences, and they're showing our models to the people at these press conferences, sort of trying to explain what we were saying about what the lockdowns would look like and how much infection there is going to be in the near future. So this is the head of the health department in Ohio, Dr. Amy Acton, and this is the governor, Mike DeWine. And as I said, early on, it was really important to sort of explain to people what does this pandemic do. So how does the epidemic curve look like? People didn't completely understand that. What are the reasons, for instance, for trying to stay away from each other, and then how exactly a pandemic can progress moving into the future. So this is how the pandemic looks like in Ohio right now. You can basically see that starting from March all the way up to the 7th of November, we have had a number of different waves. So there was a wave 1, a little bit of a wave 2 later on. There was this huge wave in at the end of 2020 and the beginning of 2021. Then that's where the vaccination started. There was a little bit of a bump here because of the Delta variant, and that went down with the number of vaccines that were being rolled out in Ohio. But then after some time, when things were basically almost gone, so the epidemic was almost non-existent, it started coming back up. And this has to do with the fact that there were some subpopulations of people who refused to vaccinate. Okay, at least that's one of the hypotheses. So then it basically went up, and now it's on its way down. Hopefully it will continue to do that, and hopefully in Italy this picture will be much lower now.
So when was the last peak?
The last peak over here is sometimes in September. So you basically see that it keeps going.
Oh, okay.
Yeah. So again, we believe that at least in Ohio things are calming down. So we are on the right side of this epidemic. So what I want to talk to you about is, first of all, the idea behind making the model of a pandemic, and then a little bit about the mathematics of how and why this worked the way it did. So these are just some examples of fits that we provided against the data. So this is cumulative infection. This is on a particular wave. So this was not the most recent one. This was the one over here. So this was how the wave looked like when you smoothed out the empirical data, and this is basically what we were predicting with our model. So it's not super precise, but as far as statistical analysis goes, it's very often quite reasonable. So what we did, though, and you can basically see it here, we tried to abstract out the model from the population study. So basically, very often when you are looking at this notion of an epidemic curve, you're counting people, right? You're basically building this epidemic curve, an empirical epidemic curve, by simply computing the number of new infections every day. And then you move with this. This is usually what's reported as a statistic. So what we did in our model, we actually did not like to use that approach because it's not always completely clear whether we are counting everybody that we should be counting. So we make this into a more abstract setting in which we computed something that we call the density of the epidemic. And I will explain in a moment what this means. Okay? So this is a normalized density of infection. And that was the object that we worked with. The advantage of this density of infection object is that you can actually then apply it and compare it with the number of different epidemics, because this becomes then not dependent on the counting. So it doesn't depend on the size of the population. So in fact, what we did was a little bit different in the sense that our model was a network model. I will not talk about this too much because it's irrelevant for the main ideas that I would like to present today. But the network model has this component in it which basically attempts to deal with the heterogeneity. So what I mean by this is that in the network setting, not everybody is equally likely to be infected. So if you have an infectious person, like we would have, say, here in the room, for hopefully we do not, but if there was one, then, you know, with some level of approximation, you could argue that then if this person is centrally located, they can kind of equally likely infect everybody else in this room and they stay here for a long time. In the network model, this is not the assumption. We are assuming that there is a structure to individuals who are a part of the epidemic, and then this structure will affect how likely a person is to be infected. So you can only be infected if you are a neighbor, in some appropriate sense, of a person who is infectious, and you happen to be susceptible. Okay, so it's different. So for instance, I'm just showing this table in order to give you an idea what went into these models. So this was fairly complicated in the sense that there were a whole bunch of network parameters. We computed the average number of neighbors, the size of the network, the rate of dropping connections. So if you were interested in understanding what was the lockdown like. So the lockdown in the US started in March, as I'm sure it did in Italy, more or less. And then it lasted for at least several weeks, more like a month and a half, ultimately. But then there was a big pressure to reopen. So then we were asked by the governor's office, so can you give us some idea about how much this lockdown actually changed things? So what was the effect of these lockdowns? Can you put it into your network model and try to estimate that parameter? So that's basically what we did. And again, this is a little bit more complicated model, and it's maybe not worth it to spend too much time on some of the details. The point is that the idea that I will try to explain really very neatly fits into this network setup and makes it a little bit easier. In fact, it turns out that using the network models just makes the numbers a little bit more in sync or similar to what we would see in real life. So this model just becomes better. But mathematically, the idea is really the same. So I will focus on a slightly simpler version, and we'll assume that we have what we call the uniform mixing. So this is, the model obviously at some point started introducing vaccinations. So, you know, we have had these different schedules of vaccines. Again, in the US, it was based on your age, as I think it was also, at least initially in other countries, in Italy also. So the idea was that you would be allowed to get vaccinated, then everybody who really wanted to be vaccinated would get vaccinated within the period of time that typically it would take to get both 2 doses. In the US, we were mostly using Pfizer and Moderna vaccines. So 2-dose vaccines about a month apart. And then everybody else who did not want to get vaccinated wouldn't. So you sort of would expect to have some kind of asymptote or a plateau in the number of people who would take the vaccine in different ages. So then building this in also makes this model much more complicated, because then we need to sort of build additional categories of people at different times. Getting vaccinated, what does it mean to get vaccinated? Well, you are at least partially immune to infection, but only partially, because there is a vaccine linkage. So you, again, there is another component which makes this a much more complicated model from what we originally had. I will not talk about it also. But just to give you an idea, that this seemed to be reasonable. So Delta variant was about here, and we were using at this time, this is model that was done in January or February, and we were asked by the governor's office to see how the Delta variant would impact the model and the amount of infections. So we said, look, if people will continue to be vaccinated, then there will be a sort of a tension between this vaccination process, which will immunize lots of people, and the fact that the variant, the Delta variant, is much more infectious. So there will be an increase in the rate of infection. And this fight will result in this bomb. It will be only temporary, and it will basically last for some period of time, and then things will continue to come down. And, you know, depending on how much we believe that the Delta variant would be more infectious, you would have either higher or lower bomb. I want to show you, and this is exactly here. So we were doing these projections maybe at this time, and we were finding these bumps. So this was exactly as we predicted. Now, more or less at this time, we stopped making predictions whatsoever. So we never really looked further beyond that point into what happened to the Delta variant. But obviously, after a while, the Delta variant really became widespread. And even though there were very, very few people initially infectious with Delta variant, there were also lots of people who did not vaccinate. So at the end, the Delta variant won, and with some new mechanisms for infection, it created this next wave of the pandemic, which we are in. Okay, very good. So I would like to talk, so this is not an epi talk. I am pretty much done showing you slides related to data, at least for now. I would like to tell a little bit about the mathematical idea which is behind this model that we developed. It's a very simple idea, but potentially usable in a number of different circumstances. So the notion is that this epidemic modeling really can be divided into two subcategories. You either do something which is called ecological modeling, build ecological models, which means you're aggregating up some empirical data and you're modeling the aggregated data. So in some sense, you're looking at averages. You're interested in an average behavior. Or you could try to go to the other extreme and you could try to say everybody is different and we're just interested in how these different people are interacting with each other. That basically leads to this notion of agent-based models. So that basically is a way of trying to understand individual dynamics from the viewpoint of this little agent who is, or she, an entity, some kind of stochastic entity that is contributing with his or her action to the overall behavior of the system. Now, these models are relatively easy mathematically to understand, but they are obviously very simplistic because they are only looking at averages, right? The fact that I will tell you that you're not going to get sick on average doesn't really help you if you are interested in understanding your own risks, right? These models are better for thinking about individual behaviors, but they are very difficult to work with because they are super difficult to calibrate statistically, meaning that they will have many parameters that are very difficult to keep track of. And it's not always clear how would you learn parameters from the environment in order to run good simulations. So very often people would just run a simulation of agent-based model and hope that they will be able to reproduce something that they have seen in real life. But it's not always clear whether this reproduction is real or whether this is just some kind of derivative, if you will, of the complexity of the system. So if you run a different simulation with completely different set of parameters, you might end up with exactly the same output, and you never know which one of the two would be the right one. So that's the danger of agent-based models in principle. So what we did, we took some things out of both of these compartments. So we tried to deal with individual level risks, but we tried to use a notion of an ecological model, because ecological model is much simpler to track mathematically. So ecological model that we have used was based on this notion of a stochastic process and on the notion of the so-called SIR stochastic process, to be precise. So there is a beautiful theory of so-called stochastic reaction networks, which allows you to build complex dynamics by means of thinking about entities in that dynamics as molecules of gas that are in some closed compartment interacting with each other by bumping against each other. And then if two molecules of certain type bump against each other, they react. And as a result of this interaction, there is some change in the system. So in this very simple model called SIR, you have two types of interactions. One of them is what I would call an infection. So a molecule of type S, which would stand here for a susceptible individual, interacts with an infectious individual, molecule of type I, in order to create an additional molecule of type I and remove the molecule of type S. So another way of thinking about it is that you basically relabel this molecule of S into a molecule of I. And then at some point, these molecules of I either recover or die. In either way, they are removed naturally from the system. Okay, so the important component in here is this lambda 1 and lambda 2, which are known as the rates. So the idea is that these rates obey something which is called the law of mass action. And this is what I referred to earlier as the random mixing. So the idea is that in this compartment, in this closed container of these gas molecules, these molecules basically are free to move around the compartment, and they're equally likely to bump into each other, regardless what types of molecules these are. So that's like random mixing. That's basically like saying that if you have someone who sits, in the middle of the group and is infectious, then that person has equal access to everybody in the group. Again, this is not true in COVID, but for the purpose of illustrating the idea, I would just assume in this simple example that that's the case. So that allows us to build a model which uses this sort of formalism of biochemical reaction networks in order to describe the ecological system, the ecological model. So I'm gonna probably skip over this a little bit. So the idea of this ecological system is as follows, that one way in which you can simulate, if you would, an ecological system like this is by something that is known as the Selke construction. A Selke construction is a simple stochastic model of an epidemic. For those of you who went to my lectures in the summer school, you have seen this construction before. I'm not going to spend too much time discussing it. The point here is that this Selke construction is trying to explain us. It's trying to explain this ecological model, but from the point of view of a single molecule. So from the point of view of a single susceptible individual. So here, I am basically supplying for every susceptible individual in my population a random variable, which I call a threshold. And then I will compute something that I will call the cumulative hazard. And this cumulative hazard is developed in such a way that it's divided by n, where n is the number of susceptible individuals in my population. So overall, this hazard, if I multiply it by the size of my population, doesn't depend on n, it doesn't depend on the size. And if I do this, then I can basically develop a rule that will allow me to say, and this is important, at what time a single individual who is initially susceptible will become infectious, if ever. So this is the rule. So it basically says if I have this random threshold for an individual, then I can compare this random threshold with this cumulative infection pressure. And this cumulative infection pressure, by the way, is defined as a sum of all the infected individuals in the population scaled by n, okay, and multiplied by a constant. So the idea here is that I have a way of producing the trajectory of an infection by means of simply looking at who gets infected when, and then according to this, changing this infectious pressure. So this is a quick picture. Let's say that I had 5 people who were susceptible and a single person who was infectious. And what I'm doing here, I'm just plotting this quantity, this integral of the number of infected people. There was a single infected person initially, so then this simply looks like a constant times t. So it's a linear function up to here with the slope, which is beta over n. So once this line reaches the first threshold, so the smallest threshold of an individual in this population, this individual gets switched. So a label changes from S into I. So then I have a slightly higher slope of this curve from that point onward, and then one individual recovers, so it goes down, continues to go up, and whenever it crosses one of these thresholds, it changes the individual's label from S into R. At some point, it might be that I will either run out of my susceptibles, or that I will recover all the people who are my I's, and therefore I will have no longer an epidemic, and this curve will level. So then these two individuals, they will not reach, they would be survivors. Okay, so it's a simple way of building a stochastic model in which I can think about timings of these different infections as a way in which I am building my epidemic. Not counts, but timing. That's important. So what do we do? And what was really the idea behind the COVID model? The idea behind the COVID model was that this is a complicated model because this trajectory is stochastic. Because basically, I don't know how many infectious people I have at time t. This will depend on the history of the process up until that moment. So what we did, we replaced this by a deterministic function. So we took I over n, when I was the cumulative number of infections, divided it by over n, and then it turns out that by the appropriate law of large numbers, that's a well-known fact from this chemical reactions theory, this quantity actually converges to a deterministic function. This deterministic function is not explicit, it's given by a differential equation, but this differential equation is very simple. It's one of the simplest nonlinear differential equations, the so-called SIR equation. And if that is so, then the idea is that I can replace this random hazard that I called AN on the previous slide with this analog when I have replaced this I divided by n by the iota, where iota is a deterministic function, which is part of the trajectory of that equation. It turns out that it's useful to look at the slightly different version of this equation when I will write it in an integral form. And then I can see that basically what I am doing is I am recovering a hazard function. So I can, by basically thinking about this empirical hazard as being related to the trajectory of the SIR model, I can also think about S, I, and R in this equation as quantities that are related to the number of, or the probability of being infected. So it turns out that this ST function in particular can be thought of as a survival function. A survival function in statistics is basically a function that measures how long have you stayed without an event, right? So this is a tail of a distribution function. And in this particular setting, the survival function is given by that equation when I have the exponent, and here I have this limiting cumulative hazard. So that's a convenient way of thinking about my stochastic dynamics, because all of a sudden I am replacing at least some of my stochasticity with a complicated but deterministic quantity. And these quantities are sort of tracking the original stochastic system. So you can think about it this way. I have basically taken this stochastic curve and I have replaced it by its mean in some sense. And then I basically will have a process that will follow on average that trajectory, but now its trajectory is no longer stochastic. Okay, so moving on. So one way of thinking about it is I have the SIR model, I have cumulative hazard, I have density, and I have a survival function. It turns out that I can basically relate all of these three curves into some different aspects of my survival model. In particular, the S curve can be thought of as an improper survival function. Okay, so if I do this, then I basically am reaching something which I call the transfer model, in which I am moving away from this notion of counting people who got infected into the notion of counting or computing times when infection happens. The computing times when infection happens, it's a better way for me to think about the problem, because that makes it independent of what happens to everybody else. I have now made this a model in which the hazard function or this infectious pressure from the cell key construction becomes deterministic. So all of a sudden, I have made these individuals' fate independent of each other. So I can just focus on a single individual and I can say your probability of being infected by time t is basically little s of t. So, or with some adjustments. So another way of thinking about this is that I am really interested in something that I call the transfer process. So I am now forgetting about my population. I'm looking at the single individual, and this single individual has the following choices. If that individual was an I initially, then at some point this individual will recover, and that will be the end for that person. If this individual is an S, then they have the following choices. They can be infected with some probability, and I will call this probability tau, or they can stay uninfected with probability 1 minus tau. If they stay uninfected, they're safe. These are the survivors. These are the people who never got infected. If you got infected, then based on these differential equations, I can actually compute the density of that infection time. And that will allow me to compute the timing of infection and then the timing of recovery. It's not very difficult to see that from what I told you, it has to follow that the timing of recovery, so the timing between the infection and recovery, this holding time is exponential with the appropriate parameter in this model, in this simple model. So mathematically, it's very tractable. And it allows us to basically build a cell key construction-like simulation in which, instead of following everybody in my population to build this cell key trajectory, I'm just following some random number of people, and each of these individuals is basically endowed with these probability laws. So for this, for all of these individuals, I just need to simulate two events, the infection and then recovery. Okay, so the idea is that I can somehow build this cell key model, which is very complicated, in an incredibly cheap way, because I can just run these independent trajectories and I can compare this to what the original trajectory looked like. It turns out, even though it sounds kind of fishy, that this is actually mathematically a very sound approach. And I don't have time. Okay, maybe one last thing before I move on. And it also has an additional advantage, and this advantage is that I can write very easily something which is known in statistics as the likelihood function. So I can basically build a statistical inferential model, meaning I can try to recover the parameters of my models. These typically, the parameters would be the initial conditions and the rates of the reactions, for instance, in this model that I've mentioned. And this likelihood function is very simple because it consists of independent units of these individuals that are basically subjected to infectious pressure. So if I have that, I can basically build an expression like this. This expression is nice in the sense that it looks simple here, that the difficulty is hidden in the fact that F and that F tau here is given by a solution of a differential equation. So basically, I have to solve differential equation in order to be able to evaluate this expression. But it's still not that bad of an equation, and it turns out that it can be done efficiently. And the other thing which is important here is, because I am concentrating on these agent-like single individuals, I no longer need to take care of the entire population. So I am not keeping track of how many people did I have in my population to begin with, right? I am only keeping track of some, random or not, but number of individuals for whom I am following the timings of their change of their status. And this actually led to an interesting algorithm that we have used at Ohio State, at my university, for keeping track of the pandemic on campus. We literally picked up a sample of students, and instead of looking and asking everybody what's going on, we would just have these people send us an SMS or send us whenever they would get sick. And what we were looking for, we're looking at the timing when people got sick. If there were lots of people who were sending an SMS close to each other that they are sick, that means that there was a very high infectious pressure. And based on that, we were able to actually recover some of the parameters of that infection. So this was based on the sample of students who were making recommendations then to the president for staying or curtailing some of the activities of the university. Ohio State actually stayed open for except for the last 2 months of 2020 spring semester. It actually opened up in August and we stayed open until now. And this was one of, I don't want to take too much credit, mostly my students were involved in this, but we were certainly one of the groups that helped the president and the people who were making decisions understand what was going on. And then we had this really good way of sampling, which was cheap because it really allowed us to do this quickly for not even a very large number of students. So that's kind of the idea. I don't have time to really go into the meat of the mathematics, but it turns out that the mathematics of this approach is actually quite sound, meaning that if I look at if I know what is the size of my population, and if I have a way to somehow calculate the number of S individuals in my population, I could look at the proportion of S individual in the Selke construction model and then compare this to what it would look like if I replace my individuals in the original population with these independent individuals that use deterministic hazard function. So we have now worked with Daniela, who sits here in the first row on the paper, that kind of says that the difference between those two quantities is very small. It actually exponentially goes to 0 with the little n, where little n is the size of your population. So mathematically, if I don't know what is the population size, I can just use the likelihood function the way that I did. If I do know it, then I have actually a bound on what is the difference between the numbers that are generated by these independent trajectories and the numbers that would have been generated by the full-blown Selke construction. Okay, so these two models are close to each other in that sense, that the probability that they are away by an epsilon is basically bounded by something like this. And this is from our paper that hopefully we will soon have on archive. So I am just making a little bit of an advertising here. If anybody is interested in real mathematics of how these kinds of things are done, then this is there. Okay, so last but not least, I am running out of time very quickly. I have 5 more minutes. I would like to show you something that I've worked on yesterday night to show you, because I realized that it actually might be interesting. So we just finished a small study, actually not so small, but in the scale of the country small, when we did some interesting comparisons. I was always interested in how good are some of these public health statistics that are being presented to us by various public health officials. So if we have an infection curve that says that there is X infections, how really does this relate to the real life? So in Kentucky, in my former university, at the University of Kentucky, we have basically done a study when we were able to take a massive amount of testing of seroprevalence. Okay, so we tested one county of people living close to the city called Louisville, and we were able to test these people for whether or not they have had COVID within the last 6 months. That's basically what this test was good for. So it was not a PCR test. It was not the test that was measuring the amount of existing virus in your body, but it was the test that was measuring the amount of antibodies. So the amount of sort of memory, if you will, of your immune system of you ever having COVID. So the idea here was that this would allow you to somehow get a sense of what was the true number of infections, right? So you would, by this objective test, you would be able to also cover people who are non-symptomatic COVID, or people who were just not interested in ever showing up and claiming that they were sick. So basically they were, their infections were never recorded, which is quite a few, I would say, and at least that one would think. So Just to give you an idea, it turns out that this whole notion of DSA, we call it dynamical survival analysis, that this whole notion of replacing hazards which are random with deterministic ones, it turns out that it very nicely works with this naturally, with this zero prevalence testing. Because what do? I will just use a different dynamical system, not an SIR model anymore, but I will use something that I call an SIRT, where T stands for positive testing. So the idea is, the way in which the zero prevalence works is that once you recover from COVID, you're at least partially for a period of time immune from COVID, but it still doesn't mean that you will show up positive on the zero prevalence test. It takes a little bit more time for this immunity to kick in. So there is a shift between recovering from COVID and the time when the zero prevalence test would actually show something up. And there is also the issue that after some time, the zero prevalence test will no longer show that you're positive because your level of antibodies decreased. But that was not an issue in this study because the period of time was too short. So we used the simple SIRT model in which SIR was like before, but then we had this additional component, which we called T, that basically meant that after you recover, there was a period of time over which you were testing positive for the antibody. Okay, so we had a number of parameters here. There were 6 parameters. This model was parameterized with some initial conditions and the rates of the equation. There are some problems with these parameterizations in the sense that then it sometimes is difficult and confusing to make sure that these are what we call in statistics identifiable parameters, right? So it's different combinations of parameters can basically give you the same system. But it turns out that at least locally these things were identifiable. So what we were able to do, we're able to basically build a model in which we would say, if you are infectious, that basically means that you are Bernoulli random variable with probability T, big T, subscript little t. So at time T, this would be your probability of being positive for COVID. That means that somewhere in the past, within that window of time, you would have had COVID. And then for a period of time, you would have tested positive, and we caught you in that actual window when you were positive. So that turns out to be quite a simple, at least from the point of view of writing it down, a statistical exercise. The interesting novelty and difficulty is that this entire system depends on time, on T. So these probabilities will change as time changes. And then, you know, a way in which we were able to handle this is we had these parameters, beta, gamma, delta, which did not depend on time. So even though time was moving and we're measuring these testings at different times, we're still able to see trajectories of that equation and then change those measurements into the actual estimates of the parameters. So we did something like this, again, using DSA. It means that you're looking at the sums of independent random variables, and your likelihood function looked like this, plus this log of P when P was a prior distribution. So we basically use Bayesian models, Bayesian statistical inference in order to obtain parameters for all these 6 points. So this is the results. These were the numbers of positive tests. So this is the percentage of positive tests. The size of the circle is the number of people who were tested. We had four waves of testing, and this is basically what the model was just following the F with some. So obviously some of these are not particularly, so there is some underinflation of this model, but generally speaking, it kind of gives you the idea that you should continue to increase the number of zero prevalence with time, which was consistent with the coming out of the wave of COVID, which is basically when we were taking. So this is the comparison. So this left picture here shows you the fit of the DSA model without the T compartment, using just the public data or the data from the state of Kentucky Office of Public Health. When we fit the incidence of infection means new infection. Based on the incidence of infection, we again used this DSA model to calculate the prevalence, so calculate the total number of all people who were at this time infected, new and old. And that was the red curve here. And then from the seroprevalence model that I showed you, we actually plotted the other curve, which was the black one. And the black one was again based on the seroprevalence, and from the seroprevalence we calculated what should have been the prevalence. So what would have been the number of people in the I group in that, given at different times, given that we had that much seroprevalence at times. So as you can tell, initially for a period of time, July, maybe until October, November, these curves were really close. So there was not that much difference. But at some point, at least according to our calculations and testing, they really started looking quite different. So there was quite a bit of infection that was completely not captured by the incidence rate. Okay, so just to wrap up, DSA, this method that I mentioned, it's been used by the state of Ohio and actually a couple other states also for a period of time, to help with understanding the dynamics of the epidemic. It was nice because it did not require reconstruction of the complete process. So we basically never had to worry about whether we counted everybody or not. We were just looking at randomly selected individual and times. It can handle changes in parameters. I didn't talk about this. It also could be used in the network setting. I didn't talk about this, but it could. It turns out that the error between the DSA model and the true stochastic trajectory follows an exponential bound. So it's a really, really good tight model. And it's flexible. It can be used to predict or make some predictions about the dynamics of an epidemic from all sorts of data. You can either use the data on incidence, which is typically the data about new infections. You could use the data on prevalence, which is often the data that you obtain from the PCR tests. If you're traveling, then you are asked to provide a PCR test, at least when you go to the US, even if you are vaccinated. So the idea is that both incidence and prevalence could be used as inputs into this model, but so can be seroprevalence. So can be this testing for antibodies and the fact whether or not you have had COVID in the past number of years. So it's a flexible method. It seems like the idea is completely general and can be used for many other things. But it so happened that we just tested it, whether somewhat accidentally on these COVID pandemic curves. So thank you very much. The people that I would like to acknowledge from my lab or my colleagues from Ohio State, and then some of my colleagues at Princeton who helped initially. There was lots of computations involved in building these models. So the people from the applied math at Princeton helped us initially quite a bit with this. And I would like to acknowledge Daniela, who has helped me with some work that I didn't have time to talk about, but I hope that some of you at least will be interested and you will bug in about this later on. So thank you very much. These are some basic papers that apply some of these ideas in different settings, not to COVID specifically. Thank you for your attention. It's been a pleasure. I would be happy to take questions.